Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Today, I want to give you the last in a series of 3 videos where I show you how the representation theory of tori can be used to study the representation theory of Lie groups more generally. And more precisely, the title of this video is Finite Dimensional Representations of SL2C, and I want to give you a complete classification theorem for these finite dimensional representations. Now, this theory is extremely important in representation theory because it turns out that it doesn't matter what Lie group that you want to study. If you want to study the representations of it, then you'll need to know about the representations of SL2C. So not only is this in some ways the simplest example of a noncommutative, simple complex Lie group, but it also is used to study all the other ones as well. And one thing that I really want you to sort of get out of this video and out of this series is the fact that because of the torus symmetry that we're using here, you can actually reduce things to a combinatorial sort of a problem. Okay, so I want to try to emphasize this point. Okay, so let's get into the details. Okay, so what is the torus viewpoint and how do we use the torus symmetry? So we basically use the theory of weight spaces. So if you don't know about this, maybe you want to look at my previous video in this playlist about the weight space analysis of representations of SL2C. But let me just remind you briefly what's going on. Here we'll have some finite dimensional vector space V over the complex numbers. So it will be given by this group homomorphism, in fact a morphism of complex Lie groups, rho from SL2C to GLV. Okay, and we're going to use torus symmetry. So where does the torus come from? The torus is going to be just the subgroup of SL2C consisting of the diagonal elements. So they're just the diagonal matrices of the form zeta, zeta inverse on the diagonal. Zeta is any non-zero complex number. So this is, of course, isomorphic to the one-dimensional algebraic torus C cross. That's the torus that we're going to use. And remember, what you can do is you can restrict this representation to this torus. And since we know about the representation theory of tori, essentially this vector space here decomposes into the simultaneous eigenspaces. So this is a direct sum of Vn. Okay, so each of these Vn are eigenspaces for all of these elements of the torus. Okay, so just to remind you what this means, if you let this particular matrix act on an element of this Vn here, it just scales that element by zeta to the n. Okay, so of course, if you change the element of the torus, it'll scale by a different eigenvalue, but it doesn't matter what vector you pick inside Vn. The action of any torus element, any diagonal matrix inside here, will just scale it. Okay, so that's telling you about all the actions of these diagonal matrices. So now we just have to say, how does the rest of SL2C act? And that's given by the infinitesimal actions of the upper triangular bit and the lower triangular bit. So just to remind you about the weight space analysis from my previous video in this playlist, what we're going to do, we're going to introduce the infinitesimal actions E and F. So firstly, let's look at this 1Z01. That's going to be a determinant 1 matrix inside SL2C, an upper triangular one, which is unipotent. Okay, but we're going to write this as a exponential of 0Z00. Okay, so that's a typical way to do that. And this emphasizes the fact that the map from Z to 1Z0Z is going to be a group homomorphism. So that gives you a basically a subgroup of SL2C isomorphic to C, the additive group C. And when we apply rho to it, we get some one parameter subgroup inside there. Okay, so it's a function of Z. So we can differentiate with respect to Z. Okay, so you have this curve inside GLV, okay, in the sense that's one complex dimensional, and we can differentiate Z equals 0, and that gives you the infinitesimal action. Okay, that's the upper triangular bit. The lower triangular bit, you can do the same sort of thing, except for now you exponentiate 0, 0, Z0. Okay, that'll give you the same matrix, except for the Z now is in the bottom left corner, and you can differentiate at Z equals 0, and that gives you that quantity f there. Okay, so let's just think about what types of objects these are. So this row of x, okay, it's going to be elements inside here, and basically as z varies, you'll get a different element inside here, and you're differentiating that. Okay, so you're taking the limit of difference quotients inside here, so you'll get some linear endomorphism of V. So E and F are just linear endomorphisms of this V. So the data to describe this row now is written purely in terms of this V, okay? It's this weight space decomposition and two extra endomorphisms E and F. And then, well, what can E and F be if you want to have such a representation? Well, they can't be arbitrary. They are constrained because of the way that matrices of this form, and of this form, how do they commute? Okay, so they don't actually commute, okay, but they skew commute in a very precise way. And to encode those conditions, we have the following two conditions here on E and F. So the first thing is that E maps Vn, this eigenspace, simultaneous eigenspace Vn, to Vn plus 2. F maps Vn to Vn minus 2. Okay. So that's telling you how E and F interact with the action of the torus. How do E and F interact with each other? Well, it turns out that EF minus FE is going to be the infinitesimal action of the torus. I'm going to call that H, and to remind you what the infinitesimal action of the torus is, well, let's look at this torus and apply rho to it to give you a one parameter subgroup inside there, rho of zeta 0, 0, zeta inverse. Okay, this is for zeta inside C cross, okay, and you want to look at the identity there, which is zeta equals 1. So you differentiate with respect to zeta and evaluate that as zeta equals 1. That's the infinitesimal action of the torus here. Okay, so that's the equation that you have. If you want to write this out without using the derivative quantity here and something completely linear algebraic involving the weight spaces, well, it turns out that the action of H, okay, because we know that H preserves each of these Vn's, right, these are eigenspaces, it's very simple. So if you restrict this H to any particular Vn, it's going to be just a multiple of the identity. Which multiple is it? It's going to be n times the identity. Okay, so where n is the weight of this weight space, okay, Vn. Okay, so that's the way we're going to view a finite dimensional representation of SL2C. Okay, so let me now introduce the combinatorial picture, which really shows you how the torus symmetry can be used to reduce the study of these representations to pure combinatorics. Okay, so what we're going to do is we're going to have some sort of visual picture of this V, okay, which is combinatorial. We're just going to list basically these weight spaces. So let's suppose we have one Vn, and I'm not going to list them all. I'm just going to start with this Vn. Let's suppose you have a Vn minus 2 here, a Vn minus 4 here, okay, and so forth. Okay, I've skipped Vn minus 1 and Vn minus 3. You'll see why later. Okay, and I haven't written any past here, and well, I guess you can go further to the left as well, and you can go further to the right. I just haven't written them in. Okay, so what we're going to do is we're just going to look at submodules of this. Okay, so we're going to take such a representation, and we want to look at a submodule because we want to work out firstly which ones are the irreducible or simple submodules. Okay, so if you have an irreducible module, okay, then the only non-zero submodules are the whole thing. Okay, so the way I'll do it, I guess the cleanest way to do it is to consider a submodule by starting with some non-zero vector inside there, and then you just apply all the elements of the group to see what type of subspace it generates. But from this weight space viewpoint, remember, any submodule also has to be stable under the data that's here. So firstly, it has to have a weight space decomposition, okay, and the weight spaces are already given here. So in other words, it's got to be some subspace of this, which is a direct sum of subspaces of each of these weight spaces, okay, and it also has to be stable under E and F. That's what would happen if you have some sort of submodule. So let's start with a non-zero vector, or better still actually, the span of a non-zero vector. So a star here is going to mean a one-dimensional subspace. So suppose you take some weight space, we want to generate some sort of a submodule of this vector, representation, and we're going to start here. Okay, we'll just start there. Okay, so what we're going to do, we're going to see, okay, if you have a submodule like that, what other vectors must it contain? Well, so the first thing is you can act on it by these elements of the torus. That will just scale it. Okay, so that's what you have. I guess the other thing to realize is that, yeah, if you have a non-zero submodule of this V, remember it has a weight space decomposition. So that means that it's a direct sum of subspaces of each of those. So we can assume if there's a non-zero vector, there's a non-zero vector inside one of these weight spaces. Okay, so that's the first thing. Now, what else? It's also closed under E and F. So let's hit it with E. Well, what does E do to this Vn minus 4? Well, it sends it up to this weight space Vn minus 2. So this vector there will get sent over here by E. Okay. And then, well, this is one-dimensional, so the image is either one-dimensional or zero-dimensional, in which case this is going to be the zero mark. Well, let's just suppose, for sake of argument, that this is one-dimensional. So you have another one-dimensional subspace here, okay? So any submodule containing this one-dimensional subspace has to contain this one-dimensional subspace. Okay, let's keep going. Let's hit it with another E. Now you map over here, okay, with another E. Okay, and let's suppose that that's also one-dimensional. So you can keep hitting with E, and all of those vectors have to be inside your submodule generated by this one-dimensional subspace. But this is a finite dimensional vector space, and so these weight spaces don't go on forever. So at some stage you have to get zero. Suppose the time when it goes zero is after this Vn. So this is going to be non-zero, but when you go to here with E, this here, it's equal to 0. Okay, so that's where you stop. I'm going to give this vector a name. I'm going to call it little v. So now we've seen in this particular picture, we have at least a three-dimensional subspace that has to be in the submodule generated by this one-dimensional subspace. So what else can we do? Well, now we can also apply F, okay? So remember, if you look at the span of these three subspaces, this is closed under the action of the torus because this is a direct sum of weight spaces, okay? So to be closed under the action of the torus is quite simple. You just need a sum of subspaces of each of these weight spaces. So the main thing we want to check is closure under multiplication by E and F. So we've looked at multiplication by E, but what about multiplication by F? Okay, let's suppose we multiply by F this vector here, okay? So we're going to go back because F sends Vn to Vn minus 2. It will land back in there. And let's just have a little look and see where it lands back. Okay, so we're going to go back like this. F. Okay, and it's going to be something like this. We're going to look at this module here. Okay, and then what do we have when we look at this module here? This vector here, rather. Okay, let's have a look at this vector. And what we're going to do now is we'll have a look at that. And then I guess we can also map by E as well, back over here, and get more vectors. So let's see what happens when you go around like this. Okay, so they're both E's. Okay, we're going to go around like this. And the way we're going to do that is, well, we've used these two conditions, but we haven't used this condition here. So I want to see what's the effect of this condition here. So when we go around like this, well, what we have is basically FE. So that's this EF here. And we know that when we subtract FE, So that means you do E first, and then this one, you'll get H, which is, in this case here, N. Okay, multiplication by N. But going around this way, right, this term here, when you go around here, is going to be 0. So this EF, so going around like this, this is E last and then F first. Okay, so this EF here, if you go around like this, what is that? That's just going to be N, because the other term is 0. So that's just N times the identity when you go like that. Okay, well that's good. So you know something about what that means. If that's N times that identity, that means that when you map over to here and you come back, that's N times the identity. So actually this will map back to this one-dimensional subspace. If you apply F here to this, you get to this one-dimensional subspace. You apply E, you get back to this same one-dimensional subspace. Okay, because that's just multiplication by N. Okay, well let's do the same thing and multiply by another F here. Okay. Okay. And then you can also go ahead and you can multiply by E. Okay. And let's see what happens. Do you learn back where you started, or do you get something different? Okay, so that's what you can check. And we can do the same, use the same condition here, but applied to this one-dimensional subspace. Okay, so what's going on? So firstly, if you do this going around like this, that's the one we want to see. Like, do you come back to this one-dimensional subspace or not? Well, it turns out if you do go like this and go like this, what's happening? So remember, going around like this, essentially, because when you go here and then here, this is just multiplication by N. Of course, if you go here and then here, this has to be multiplication by N as well. Okay, that's the only possibility for what that is. So this time here, this is multiplication by N. And then the sum of this one here and this one here is multiplication by, well, here you're in the weight N minus 2, so it's multiplication by N minus 2. So here you'll have N minus 2, and you want to know what this one is here. So that's going to be N plus N minus 2. Okay, so that's what that is going to happen there. And you can keep going. And then at some stage, of course, you have to get 0. Okay, and then you can stop. But one of the things that you'll notice here is that from this process, you'll find a submodule. You start with this V, you apply F, okay, that's going to be in there, but if you apply E, you won't get something new, okay, you'll come back to where you started. You can apply F again, but if you apply E to that, you'll just get back to where you started, and so forth. So you'll get a string of one-dimensional subspaces, okay. This one here, if you apply E to it, you'll get 0, and then eventually, if you apply F to the last one, you'll get something that's 0 as well. So that's the combinatorial picture that I want to show you, and it tells you the following. Okay, so what we're going to do, what's the upshot of what's going on? So firstly, you can pick a V inside some weight space, which is non-zero, some V like that, and it's such that if you apply E to it, you get 0. So that's what we found here. We chose any vector here. Okay, we just kept applying E until we got 0. Okay, so the last one before you get 0, we call that V. And what we're kind of trying to do is we're going to generate some sort of submodule by applying E's and F's. Okay, and the point is that to be stable under the torus just means that you have a direct sum of weight spaces. So you just need subspaces of each of these weight spaces. So we apply F, and then F, and F, and so forth. And then what happens if you apply E to any of those one-dimensional spaces that you get? Well, do you get something new? No, you just move back to one of these other one-dimensional subspaces. So that's telling you the following. We obtain an SL2C submodule, which is basically gotten from V by multiplication by some polynomial in F. Okay, so what are all these vectors here, given by these stars? Okay, okay, they're going to be, what are all these one-dimensional subspaces? They're spanned by V, F of V, F squared of V, F cubed of V, and so forth. So eventually you get some polynomial in F over C times this V. So I forgot to write a V here. Okay. And the only thing that's kind of interesting is that, well, when does it stop? Okay, so that's the question. Well, I guess you can kind of tell what's happening here. Right here, you're multiplying by n. And if this n is, if this n is non-zero, then this can't be the zero map. If going around like this, it's n plus n minus 2, and that's non-zero, then there's no way this can be 0. So when do you get 0? That suspects that you need to be able to add n plus n minus 2. So the next one here will be n plus n minus 2, that's this here, plus n minus 4, which is this number here, and so forth. So we add n plus 2, n minus 4 plus, and we want to get 0. And when does that happen? Well, if you think a little bit about it, when you get zeros, if you keep subtracting 2's from here, eventually if you start at n, there'll be a term which goes to minus n. And of course, if you add all these terms, the minus n here cancels with this n, and the one just before this one will cancel with n minus 2 and so forth, so you get 0. So that's the time when you get the 0 here. So that's when you stop. Now note that this v, fv, f squared v, all of these, because they're in different weight spaces, they'll be linearly independent unless, of course, you get 0. Okay, so when you go too far, you get 0. So when do you get too far and get 0? Well, how many terms are there here? So I guess the n plus 1. F to the n plus 1 of v is equal to 0. Okay, so that means f to the nv is the last one that you have. So the dimension of cf of v is equal to n plus 1. Okay, so you get v up to f to the nv. Okay, that's the last one. And then the other thing that you should notice is that, of course, these powers of f times v, they're in distinct weight spaces, and f to the iv is in v subscript n minus 2i. It has weight n minus 2i, and that's just basically an application of this formula here. Okay. So this is the sort of key observation that you have here. The only thing that I want to mention also is that this is actually an irreducible submodule. Okay, this one here. So what you generate, if you use this procedure, you start with such a v, such that when you apply e to it, you get 0. And then you just apply f as many times as you can until you get 0, okay? And you look at span of that, that's an irreducible submodule. Okay, so why is that? Okay, so suppose you look at this module here, and I want to show that any non-zero submodule has to be the whole thing. Okay, so let's take a non-zero submodule. So remember, any non-zero submodule has to have a weight space decomposition. Okay, so you can find a non-zero vector in one of these weight spaces. But all the weight spaces here, right? These are in different weight spaces, and they're all one-dimensional. So so if you have a submodule, it has to contain one of those one-dimensional subspaces. Maybe this one here. Let's just suppose it has this one here. Well, if it has this one here, when you apply e to it, you'll get this one here, and then you'll generate the whole thing. Okay, so that means that, in fact, any submodule that you have of this submodule, any submodule they have that's non-zero is going to be all of this. So it's irreducible, in fact. Okay. This is rather nice. So if you look at this construction here too, it says a lot more too. Actually, the isomorphism class of this CF of V, this submodule I constructed, is completely determined by n. And this n, of course, is just the dimension of that module minus 1. Okay, so why is that? So how do you work out what type of SL2C module that you have constructed here? Okay, how do you work out what that is? Well, to work out what that is, you just have to give its weight space description. So you have to give the weight space decomposition. So here's the weight space decomposition. It's given, right? This V is in V subscript n, and then FV is in here, F squared V is in here, and so forth. So that weight space is completely given. And then you also have to say, how does E and F act? Well, you can kind of see how E and F act here. So F acts just by, well, if you let F act on this V, it will go to FV. If you let F act on FV, you get to F squared V, and so forth. So you know the action of F rather. And how does the action of E work? Well, the action of E is completely given by this formula here. So that's why you also have this fact like that. Okay. So that's completely described what E does. So once you know what EF does, and also what is the weight space decomposition, then you know what that irreducible, or rather that representation of SL2C here, which is irreducible. Okay, so that's really great. So you've got a lot of information about this. Okay, so what does that mean in particular? So this CF of B, if you can find any irreducible SL2C module, okay, which is dimension n+1, then it has to be this one. And there's a simple example of that. If you look at CXY, you can let SL2C act on X and Y, okay? So if you want, you can see the action in my video on the torus analysis of representation, okay? And so what this is just the degree n homogeneous forms in X and Y. So it's the span of X to the n, X to the n-1, Y, all the way down to Y to the n, okay? And if you want to see what happens here, of course, this is also the weight space decomposition. And essentially, if you look at the E and F, they'll just move up to scalar, these monomials, one across or one back, okay, depending on whether you use E and F. So in fact, we know precisely what now are all the irreducible SL2C representations. And they all lie inside the polynomial ring here. So that's rather nice that you can get it from that polynomial ring. Okay, so let me just finish off with the final theorem. Unfortunately, I won't be able to describe for you the proof of this, okay? But the final theorem, which classifies all finite dimensional representations of SL2C, is the following, okay? So if you have a finite dimensional SL2C module, it is firstly isomorphic to a direct sum of irreducible modules, okay? And now we've classified all these irreducible modules. So what are all the irreducible modules? The latter all have form CXYN, as I've described here. And n here is just any natural number. Let me just say a few words about the fact that this is isomorphic to a direct sum of irreducible modules. This here, if you've studied the representation theory of finite groups, okay, over the complex numbers, this is a result that's familiar from there, okay? Everything is a direct sum of simple or irreducible modules when you look at modules of a finite group, okay, and their complex representations that are involved. And the way that that's proved is usually by using the averaging trick, okay? So this is Matchka's theorem, which allows you to prove this. So you can do something similar in the theory of Lie groups, okay? So to average though, what you want to do is you want to integrate. And if you want to be able to integrate over the whole group, you need a compact group. And so there is a general theory that allows you to do this. The basic idea is that firstly, inside here, you do have a compact group. It's SU2. And so you can show that if you look at SU2 submodules, then you always have this what's called semi-simplicity, okay? You've always got this decomposition into irreducible modules. And then you can lift to this SL2C, okay, by using what's called the Weyl Unitarian trick. Okay, so unfortunately I can't say more about that, but this is kind of the standard theory in Lie groups. So that really sums up the final word on representations of SL2C, at least the finite dimensional ones. And I just want to wrap up by just saying some generalizations of what happens, okay? So, well, this is just SL2C, what happens in general, okay? So the point is that this theory generalizes to SLNC. And in fact, it also generalizes to other simple algebraic groups. And let me just say, well, what types of things change and what goes on? Okay, so the first thing is that here, what do? We use this torus here, okay, for SL2C. If you have SLNC, well, you can also look at all the diagonal matrices, okay, and they'll commute with each other, so you'll get some sort of a torus as well, but the torus is a lot larger, okay? So when you look at these weight spaces, okay, it won't be indexed by Z, okay? It'll be indexed by some number of copies of Z, Z to the something, okay? So that makes it a more complicated combinatorially. And the other thing that makes it more complicated combinatorially is that once you have the weight space decomposition, what else do you need to do? Okay, so here we looked at the upper triangular bit and the lower triangular bit, and well, the upper triangular bit, there was only one sort of like generator here, and for the lower triangular bit, there's one generator F. Now you'll have a lot more generators for the upper triangular and the lower triangular bit, and they'll be working in all sorts of different ways. So the way these arrows will go will be much more complicated, how they'll map from one weight space to another. But the same type of analysis goes through, okay? The idea is the same, okay? But the combinatorics is more complicated now. But other than that, what that will give you is a complete description, okay? If you follow that through, you can get an analogous theorem to the one that you have here, okay? And you can completely describe all the irreducible modules, okay? So that's how we use torus symmetry to study finite dimensional representations of SL2C in particular. I hope you enjoyed this adventure in pure mathematics.